7.3. We're now ready to do the whole algorithm. So by the end of this, we're going to look at algorithm 7A, which is the affine scaling interior point method. There are several interior point methods, just like for the simplex. There are multiple variations of the simplex. We learned one. There was you coded one, but you also talked about the revised simplex, which was an advancement, and then the upper bound, lower bound. And then beyond that, there's a dual simplex, there's a primal dual, so many different variations of it. And this is just one variation that he's teaching us. This is the most basic, the simplest. I'm not going to make you program it. You just have to know how to do certain steps of it and know the idea, know that it exists, and when to switch. That's helpful if you're working for a client. You may need to switch from one algorithm to another, and knowing that they exist and that you can do that in the software. Okay, so we had finished 7.2 and we had found we could get a direction vector in the new space. And at every iterate, we had to do this. We had to do this projection step at iterate t that was built based on the xt that you were at. And we had to do the same thing with the objective function. We had to keep anything from the original space. When we went to the new space, we had to hit it with that xt matrix. And so we'll do the same thing, delta x, to actually go back to the original space. The delta x, the direction vector in the original space, you have to hit it with the xt matrix. And then again, same thing with the projections. Is that improving and feasible? Okay, well, that's actually something you guys are going to do for one of your homeworks. And how do you check if it's improving? What do you have to do? That's our usual a delta x equals 0. If that is true, so that you're going to check that condition for this delta x. A delta x equals 0. And then feasible, you're going to check that C transpose times this delta x is greater than 0. And there's a few little tricks, facts from linear algebra that'll help you do it, but it's pretty straightforward. You'll be able to do it. So you will find that yes, it is improving and feasible. And so at this point, we have all the pieces that we need for an algorithm. We have an initial interior point. So every component is strictly greater than 0. That, again, could be a problem in and of itself. Let's assume we got that. We've got a delta x, that is our direction vector. It is improving, it is feasible. And what else? For interior point methods, it's equidistant from the boundaries. It was by design created that way. So what's next? The next piece of the puzzle is to get to the next iterate. That's xt plus 1 is xt plus lambda times delta x. So we need the lambda. That's our next thing. All right, well, let's think about a few cases here. What if every component of this direction vector, you've computed it, you've done all that work there, you got it, you look at it, and every component is non-negative. Are there any restrictions then when you're building your next iterate to get the next solution vector? Take the first one amount, which is interior and feasible. So that all is a vector greater than 0. This is a vector greater than or equal to 0. Are there any restrictions on lambda then that would keep this from being feasible? Well, if there are no negative components here, I don't have to worry. And actually, what does that mean for the problem? So no, there would be no restrictions on lambda. So, and that would imply that your LP is unbounded, right? What's typically going to happen though in practical problems that you're working for with a client, or something from our textbook that is an applied problem, if any components are negative, those are the ones we have to worry about. Because again, remember when we formed this, well, now we have a few negative components in here, just like for the simplex. Those are the ones we're going to focus in on, because we want to make sure that xt plus 1 is also feasible and interior. Here's our rule. If your lambda is going to be 1 over, so we have to form this thing in the denominator. This is a norm, and it's actually a 2 norm. Just to review, if you haven't seen those, a 2 norm of a vector, what's called x, is the square root of the sum of the components squared. So if it's an n by 1 vector here, we'll have n things. We're going to square each of them, sum them, and take the square root. That's a 2 norm. And that's what's happening here. Okay, so you can compute it either with this. If you have the delta y, you just take the 2 norm of that and then 1 over it, invert it, or delta x, the direction vector you just got, with the iterate you're at, you put it in a matrix and do that diagonal inversion. Take the 2 norm. Okay, oh, I forgot to say last, in 7.2, we had 9 B and C and 11, and then in 7.3, we're adding 2 more, 15 and 17 A and B. We're not quite done 7.3. Okay, we're gonna take a look at algorithm 7A. This is page 407. So algorithm 7A is our affine scaling for interior point methods. Let's take a look at each step and think about implications. So step 0, initialization. We need a starting feasible interior point solution. It needs to satisfy that all components are strictly positive. Any worries there? Well, yes, because just like with the simplex method, we need to now find something that solves AX equal B and is strictly positive. That could be a problem in and of itself. Again, often for these that we're just going to use from the textbook, they're given, they're just dropped out of the air, but there are their own routines to get solve step 0 sometimes. Step 1, optimality. If any component of your iterate is 0, stop. Or it says if no significant change has been made from xt to xt plus 1, you actually look at every element there and they don't look like they're changing much, they're converging, you can stop. And it's either optimal or it says very nearly so. So let's take the first case where there's a component in xt that's 0. Why would that mean stop? Why would that mean you're done? Well, if any component is 0, you're no longer in the interior. That means you're actually on an extreme point. If any component is 0, you are at an extreme point. Therefore, we know from chapters 3 and chapter 5 that optimal solutions of LPs only occur at extreme points. So you must be at an optimal solution. And then the very nearly so comes from the fact that if it wasn't exactly 0, or you looked at your iterates, and we'll show that with an example here, you're looking every iterate x0 has a vector, x1 has a vector, x2 has a vector, and so on. And you get down to maybe x100 and x101, and they're barely changing, maybe in like the 8th decimal place. Again, you're close enough, you can stop. So you can have this termination criteria. Step 2 is our move direction. So to get the delta x, remember that's this form a matrix xt of the current iterate you're at. You put it in a matrix, just a diagonal. P, that was the most expensive thing you're going to get, the projection matrix at the current iterate you're at, right? It changes every iteration you're at, and there's a different P projection matrix. CT is our objective coefficients in a vector times the xt matrix. Remember that, so it's at every iterate we're doing, every constant matrix is actually changing. This is the most work. Again, we've talked about that. It's several matrix multiplications plus a matrix inversion. It's several ON cube pieces of work. By far, the most expensive step is right here. And then our step size, we just had that up on the board. This is the direction vector times this matrix of the current iterate inverted, and then a norm. And it turns out because this is a diagonal matrix and this is a vector, you can think of it as instead of a vector matrix multiplication, the inversion's no problem. That's ON work. And really it's almost equivalent. Well, it is equivalent to doing an inner product or a dot product. So it's really ON work down here. And ON work for the norm. So ON worked, several ON cubes. And then we get the new solution, our usual update rule that we've been doing since chapter 3. So not expensive, greatly expensive. Okay, let's take a look at this on that same example, the Franny Firewood, which was the X and Y's we started with in this chapter. We were on that triangular section of a plane. And here's our initial solution, 1, 1/2, 2. Clearly that's interior. There's no components that are 0. You're going to get your change vector. Quite a bit of work. They're not showing any of that, but that change vector required the projection. That was step 2, very expensive step. Then this is step 3, right? Yeah, step 3 is the step size, computing that. And notice this is very typical of interior point method. Lots of crazy looking decimals, even on what look like nice problems that started with nice integer coefficients. X1, notice again, interior clearly. The change vector gives us another step size, and we just keep on going until we get down to, notice the difference between X8 and X9, right? They're starting to converge, it's looking very similar. That's why the convergence criteria in step 1 was saying they don't have to be exactly 0 in a change vector. It could be that your iterates X8 to X9 are within some tolerance of each other. And we do also see both things are satisfied. X8 and X9 are very close. Whatever your tolerance level is, 10 to the minus 4, 10 to the minus 8, taking a norm between X8 and X9. Or the delta X9 does have components of 0. So, I'm sorry, the delta X9 itself, not the change, the delta X9 does have a component 0. Okay, so then we can stop. We are at the optimal solution, and what does it actually look like on this problem? This is what's actually happening. In the original space, you're transforming, you're doing this transformation Y sort of behind the scenes, but we're displaying all the X iterates. And this repels us from that boundary because we're actually doing the equidistant in the Y space. And we get to our optimal solution, which we knew before was 6, 0, 0. Just visually, we could graphically find the optimal solution by looking at this. Okay. Okay, I want to work this example. This is number 16. Okay, Chief. This is number 16 at the end of the chapter. We want to maximize this function clearly in standard form. Everything's set up. Part A, they ask us several parts. In part A, they say, why is this x0 equals 1/3, 1/2, 1 a good place to start an interior point algorithm like algorithm 7A? Why is this a good idea? Oh, well, it's interior. It's clearly interior, away from the boundaries, which are 0. And the next thing they say, formulate the problem, the interior point LP at that iterate, because remember, there's an LP at every iterate that you're at because of that parameter xt in every component. So we're at x0, so we're going to form c0 times y, a0 y equals b, y greater than or equal to 0. C0 is the initial 6, 8, 10, the initial C. Okay, this is our C times your x0. You take your iterate, put it in a diagonal matrix. So doing that multiplication, we get to the new C vector in the new space, 2, 4, 10. Same thing with your A matrix. Your A0 is A times x0. Take your A matrix, 9 minus 2, 4, 0, 2, minus 2, put it in a matrix, that's A. Multiply that times x0. X0 is the current iterate you're at, put it in a diagonal matrix, do the multiplication, and here we get A0. Next question, he says, form the direction vector at that iterate. Again, always, every time at that iterate. At x0, our delta x, again, we have to add the subscripts x0, p0, c0. Go ahead and do that. You can just check. Again, p0 is the work. Put this in MATLAB, definitely let it do the computation. You don't want to be doing these clearly with these fractions, and then things are going to turn into ugly fractions and decimals. And so we get this value. Check your work. Next question. Is this direction vector that you just got in step C, is that improving? Is it feasible? That's what we need. Improvement, always check your dot your direction vector with your objective function. The only thing that's different from the simplex is we have to do this at every iteration. The C is actually changing because we're transforming the space that we're in. Is that greater than 0? Yeah, 51.02, yes. Is it feasible? Check again, is A delta x equals 0, except we have to make sure we do our A0. It will, check. Last thing you do, and we've done one iteration, we're ready to do one iteration of algorithm 7A. Affine scaling, improving search, get your step size. Our step size is 1 over delta x. We just computed that up here. Multiply that by this diagonal matrix, but in the inversion of it, so that'd be 3, 2, 1. 3, 2, 1 times this vector. Really, again, you can see that's easily a inner product or a dot product. You get 0.14, and then go ahead and get your next iterate. Get the next iterate x1. Notice clearly interior. We already checked it's feasible and it's improving, and we've repelled ourselves from a boundary. In the y space, we've actually done it in an optimal way because we're equidistant from all boundaries. But when you're back in the x space, you just see that tracking like we had the Fanny Firewood, where it was this way, right? Fanny Firewood example where you're getting repelled by the boundaries in the original space X. Okay, again, some problems to practice, doing a few iterations. I'm not going to make you code this. I'm not going to make, I just want you to know pieces of the algorithm. Okay, one more thing. We're not going to do section 7.4, but I want to show you an idea from section 7.4. So, okay, so here it is, this in this box, principle 717. This is another way of dealing with interior point method, rather than doing an affine scaling where we had an X and a Y space. This is a way where you are being repelled from the boundary by pushing that idea that you want X greater than 0, right? We want X, we don't want to be X greater than or equal to 0, we want X strictly greater than 0. And you do that by taking that constraint, which is a simple constraint, and pushing it into the objective function. This is a common idea called a penalty function. And so you're taking your original objective, C transpose X, but then you're doing something here. Notice what this is doing. So we're going to create this, it's like a Lagrange multiplier from calculus, if you remember those. But focus on this part, the ln x. What is that doing? So ln x is this kind of function. As ln gets closer and closer to 0, ln x gets closer and closer to negative infinity. It like exponentially rapidly goes down to negative infinity. So that's saying when x gets closer to 0, the contribution to the objective function is a big negative value. You don't want to do that. You want to maximize, right? And so you're penalizing the fact anytime x gets close to 0, any component of x, so the x vector, if any component's getting closer to 0, you're getting a big penalty objective function, and therefore the objective is going to not do that. It's going to be repelled by that idea. It's going to move away from a boundary. And of course, if you were minimizing, you would just negate that, right? Because opposite goal, right? Okay, so that's all I want you to know about 7.4, that idea of penalizing, taking a constraint. And we do this sometimes, like I do it a good bit for my research and apply problems. Sometimes there's several constraints and they're classes of constraints. Like this class might create, n squared constraints. This class here creates n constraints. This class creates another n squared. And maybe it's that last one here that's very problematic. Like if it just had the first two classes, maybe it's easy to solve it. But you add that third class and things get difficult. Well, sometimes what you can do with those, again, if you can identify classes of constraints that seem to be problematic and causing you issues, can you push those into the objective? And then what you're left with is the nice, well-behaved constraints. So the remaining polytope or feasible region is nice, and then you got rid of those bad ones by pushing them up into the objective with a penalty. So key idea there. And then the second thing I told you, I will come back to like why it's nice to know that there are different algorithms to solve LPs. Whole class of simplex, and there's many there. Whole class of interior point, and there's many there. And the reason interior points, like I can give you an example from my research. If we're back at this polytope here, this rankability polytope, rather than finding one optimal solution, I have an instance of problems, don't need to know the details. It's for a problem called a rankability problem, where I actually want to know every optimal solution. So often in this class of problems, I end up with an optimal face rather than a unique optimal solution. So it might be that these extreme points are on the optimal face, but also every point on the optimal face is also optimal. And I'd like to, for that particular problem, find a point on the optimal face that's near the centroid, either is the centroid or near, in quotes, the centroid, I'll take it. The reason I want something near the centroid is that centroid point actually represents a summary of all the binary extreme points, right? So if I could enumerate all of those, that is a whole problem in and of itself. Getting all optimal solutions for an LP is a open problem. It's not knowing how to do it. For certain classes, like this one that I'm working on, we were the first folks to find that we could get every optimal solution for these rankability problems and every extreme point by actually going through the interior, ending up on an interior point on the optimal face, and then building from that interior point using some logic and getting back to all of those extreme points, optimal extreme points. You couldn't have done that with the simplex. Like the simplex will just end up here, or it would have ended up here, it would have ended up here. You can restart it, randomly permute your constraints or something, so the A matrix is getting randomly permuted. They'll end up here. Run it again, maybe it's over here. But in higher dimensional space, I have hundreds of thousands of these things I'm trying to collect. So that's not going to work. But if I just switch the code and say, hey, Gurobi production code, please don't do the simplex now. Please do this interior point method by Matrosa and Yi, and it'll run through the inside and come out right here. Anywhere on this face is good for me. And then I can use some other techniques that we have to get there. That's it.